Hello everyone, welcome. I'm Nirmal Malapaka. I'm a visualization developer at Wolfram. In this talk, I'll show you some of the features we've been working on to enable fitting data in plots. In version 14.3, we introduced experimental features that make plotting fit curves easier. I'll walk you through these new plots and show you how easy it is to now plot fitting information along with the data. In this context, it will be useful to take a quick look at what has traditionally been the main paradigm for plotting curves in the Wolfram language, namely interpolation. Then we will see how it differs from regression. We will look at the new fitting functions that are used to generate the fit curves. Then I'll show you the new plotting functions we introduced in 14.3, as well as the options that extend the fitting functionality to data plots in general. We will look at how these options work with an example dataset, and I'll touch upon some basic modeling to understand the dataset we'll be using. And finally, I'll discuss some future changes and directions for fitting functionality in plots. Before we get started, I'd like to highlight a few other talks related to visualization and fitting at this conference. Today there was a talk on visualization updates by Brett. If you missed that one, I hope you can catch the recording. After my talk, there is a talk by Min on styling tabular data. And tomorrow, Julio will be talking about unified fitting and modeling that goes into some depth on modeling data. This year, we also have a visualization office hour every day of the conference. Today it will be in the afternoon, and on Friday in the morning. Members of the visualization team will be at these office hours, so if you have any questions or suggestions, please join us. Okay, with that, let me get started. Here's a grid of plots that shows the difference between the standard version on the left and the fitted version on the right. If we look at the first row, we have a list line plot of some data on the left, which by default joins the data points. And on the right is a list fit plot that shows the fit curve along with the data points. Similarly, list plot 3D shows the interpolated surface for the data, and on the right is the fitted version of list plot 3D, which shows the mean surface as well as the original data. And in the last row, we have list contour plots with the contours for the standard surface on the left and contours for the smooth surface on the right. There is also a list density version that works similarly. This is where I'd like to emphasize the experimental status of these features and note that we're thinking of changing the default behavior for some of these plots going forward. So now let's look at some visual differences between the standard plots and fit plots, and then we can look at how these new fitting features work. The thing to keep in mind is, as I mentioned before, in the standard versions of plots, the lines and surfaces use some form of interpolation. So in this grid of plots, the first two columns show the plots with interpolation order set to 1 and 2 respectively. The plots with interpolation order 2 are a little smoother, but the lines and surfaces go through every data point. And the third column shows fitted versions of the same plots. As you can see, the fitted version is a qualitatively different plot. They show both the data as well as the fit curves or surfaces where the fit element is derived from the data. But unlike the interpolated version, the fit elements need not go through all the data points or even any of them. As we will see later, it gives us the ability to focus on different aspects of data than the standard versions of plots. In version 14.3, we introduced two dedicated plots for visualizing fitted data, namely listFitPlot and the listFitPlot 3D. And for existing data plots, we introduced two options to control the visual aspects of data fitting. They are PlotFit and PlotFitElements. So between the dedicated plots and the fitting options, we can incorporate data fitting into our visualization functions. Having said that, we are still evolving the design, so some of the default behaviors may change going forward. Let's take a closer look at fitting. So here is some data, and we can plot it with listplot, and that looks as we would expect it to. Now, if we use listLinePlot, then the points are joined, and we get a line going through the data points. Interpolation works by fitting polynomial curves between the points. We can use interpolation order to specify the degree of these polynomial curves. The default setting is 3, which yields cubic curves. In this plot, we create a function using linear interpolation between the values, resulting in a collection of straight line segments. And that matches the listLine plot above. This has been the preferred way to visualize curves and surfaces in plots in the Wolfram language. But we've also had a strong convolution and correlation functionality in the Wolfram language. So let's take a look at these same data points and try to generate an alternate curve using convolution. Here we're picking a Gaussian kernel, and then we're convolving the kernel with the data, and then finally plotting data along with the smoothed version of the data as a line. So unlike in the interpolated version, we are generating a line that approximates the trend of the data. Or at the plot at the bottom here, we are using a kernel to compute the moving average of the data. Also, we are using interpolation order in listLinePlot directly to further smooth the curve. And here is an example of choosing a kernel so that the convolution hits every data point. So we're essentially simulating the interpolation case with this choice of a kernel. We've also had a set of functions in Wolfram language to construct statistical models, like linear model fit, nonlinear model fit, etc. And here's an illustration of how we can plot a curve derived from a fitted model. We're using linear model fit to construct a best fit line for the data and plotting it along with listLinePlot of the data. In version 14.3, we introduced two new fitting functions as part of an ongoing overhaul of the modeling framework. These are local model fit and kernel model fit. Local model fit uses local polynomial regression, or LOS, to fit the data. For every sample point, it involves fitting a low-degree polynomial to a subset of the data. Then the fitted polynomials are combined to form a continuous approximation of the entire dataset. Kernel model fit performs localized data fitting using a specified kernel function. It uses fixed basis expansion, which is commonly used in data analysis fields like financial modeling, where capturing local variations is critical. And just like in the example with linear model fit, here are the fit curves generated using local model fit and kernel model fit. So we generated the model based on the data, and we can simply plot the model as though it were a function. So this exercise was to demonstrate the mechanism by which the new fit plots work. It also shows that on the one hand, interpolation and fitting are technically different approaches. On the other hand, for generating curves, the decision to pick one over the other is, if not arbitrary, highly influenced by the application area. For historical reasons, we have been using interpolation in Wolfram language visualizations. With the fitting options that we are about to look at, we are starting to provide a way to take a different approach to generating curves and surfaces. So let's first look at what these new functions are and what the options do, and then we can explore them some more. The two new functions are listFitPlot and listFitPlot3D. These are the fitted counterparts to listplot and listplot3D. And by default, they plot the data along with the fit curve or surface. So here we have some example 2D and 3D data, and this is how the fit plots look. In order to extend the fitting functionality to more plots, as well as provide better control over the various fit elements, we've also introduced two new options, PlotFit and PlotFitElements. PlotFit option specifies what model to use to try and perform the fit for the given data points. So it takes the string values and generates fit elements corresponding to the specified model. It also takes a fitted model object, which is generally the output of one of the statistical modeling functions that we looked at. So in that case, you can generate the model external to the plot and pass in the model directly using PlotFit option. Here are a couple of examples that use PlotFit to specify the model used for fitting. PlotFitElements option essentially does two things. One, it tells the plot what elements it needs to draw, and these can pertain to either the data or the model that is specified by PlotFit. Here are the values that PlotFitElements takes. So for example, if we specify residuals for PlotFitElements in listplot, then we get a plot of the data along with fit curve and stems that indicate the residuals for the data. The other thing that PlotFitElements controls is the style used to draw the elements, and the way to do that is to use the second to last form in this table, where the association contains parameterized settings. So for example, if we want to set a different style for band curves, then we can add that using style key in the association corresponding to band curves. So what I thought I'd do instead of just showing you the different option settings is to try and explore a dataset using fit plots and the fitting options. Let's spend a few minutes looking at the dataset that we're going to be using and then try and explore the various aspects of the data. This is a dataset that we recently added to our data repository, and we can access it directly using resource data. It contains data for about 50,000 diamonds. It has the price of each diamond in dollars. It has 3 categorical variables, cut, color, and clarity, and 6 quantitative variables for various physical attributes of the diamond, as shown here by the tabular summary at the bottom. The quantitative variables are length x, width y, depth z. Then we have depth as a percentage and table as a percentage. Table is the top part of the diamond that catches the light. It is measured here as a proportion of the length. And depth is measured as a proportion of the mean of length and width. So those are the quantitative variables. Now let's look at the categorical variables. If we look at the cut column of our diamonds data, we see that it has the following categories: fair, good, very good, premium, and ideal. Cut is graded by light performance, polish, and symmetry, with the ideal cut having the best light performance. Light performance is measured based on brightness and dynamic contrast. Color scale goes from D, which is colorless, to Z, which tends towards a pale yellow. Color is imparted to a diamond by elements or impurities, so grades D through F are the rarest. In this dataset, we have diamonds ranging from D through J. Clarity grades are based on type and number of internal flaws in the diamond, known as inclusions. Diamonds that are free from internal and external flaws under 10x magnification are rated flawless or internally flawless. The grade decreases all the way to I sub 3, which is defined as having large and numerous inclusions, easily visible to the naked eye, which diminishes the brilliance. Those are the grading scales for the categorical variables. Now let's have a quick look at histograms for some of these variables to see if we can get a better idea of the distribution of diamonds in this dataset. Based on that, we can make some decisions about which columns we want to try and correlate and visualize using fit plots. Let's start with the quantitative variables, carat and price. There are 273 unique weights, and if we plot the histogram for the carat column, we can see the distribution of diamonds by weight. And as we would expect, there are more lower carat diamonds. And as we go up in weight, their number trails off. So there are relatively few diamonds of 3 carats and above. And by the time we hit the 5 carat mark, there's only like 1 diamond. Similarly, for price, we get a skewed distribution, which may be somewhat expected given the distribution of diamonds by weight that we saw, but we can also log transform the price and look at the distribution that way, which lets us understand the price dynamics on their own a little better. And now it looks closer to a normal distribution. Now let's look at the categorical variables, and starting with color, most of the diamonds are in the middle of the spectrum for this range of D through J. And if we look at clarity, there are very few with lots of inclusions, probably because they're discarded, and very few which are internally flawless, probably because they're rare. And for a cut, I'd imagine the demand for diamonds of higher grade cuts would skew the distribution. We can probably also assume cut is independent of carat. So at this point, we have some idea of the different factors in this data set. So we can ask some questions and try and explore them with fit plots. Maybe we can explore how each of these factors affects the price of the diamond, or in other words, what the relationship between each of the 4 C's to the price is. So let's do fit plots for each of the 4 C's against the price. Let's start with carat, since it plays a big role in how much a diamond costs. Carat against price is one of the plots that we can do directly from this data set. So let's do that. Here we are using the new syntax for plotting tabular columns against each other in this first plot. Now, if we do a linear fit curve and set the plot range to filter outliers, we can see that the relationship is not quite linear. We can also do an automatic fit for comparison, and I'm adding the 95% confidence bands using the PlotFitElements option by setting its band curves. Let me change the style for the band curves so we can see them a little better. We can do that by using the association syntax and the style and filling style keys to set the color. So this confirms that the relationship is not linear, but also that there is quite a bit of variation in price as we go up in weight. Now let's look at what effect the categorical variables have on this relationship between weight of the diamond and its price. In order to do this, we have to pivot the data so we can get it in a form that can be easily plotted. So that's what we're doing here for cut. And then if we plot the fair grade of cut against the price in this pivoted data, then we get a plot that looks like this. Here I'm plotting a local fit curve. Then we can also, again, do the same thing in terms of plotting the confidence interval. And we see a similar variation in price as the weight increases. In order to filter out some of the noise, I'm going to do a slightly different pivoting operation so that we can look at the mean price. And again, if we do the same set of plots, we see the results like so. We can also do a kernel fit to smooth out some of the wiggliness. And also I'm here plotting the two cuts at either end of the spectrum so that, you know, we can see their behavior. You can see that the ideal cuts don't fluctuate or have as much variation in price as fair, but they still have some variation. But the price seems to be plateauing out. And I'll be using this second pivoting method for the rest of the categorical variables. Repeating the same thing for color and plotting the price of the most colorless diamonds from the dataset, and by their price and weight, we can see that there is a high degree of correlation. If we draw a fit curve again, the relationship isn't linear, and we can see there is still some variation in price. Here, we're using the residuals PlotFit element and styling them to highlight the data in relation to the fit curve. And again, we're doing plots for the two ends of the spectrum on this category. And finally, we get to clarity. And let's start by picking the least clear diamond category and plot weight against price. And that seems remarkably linear to me, apart from the wiggliness because of the local nature of the fit. Let's also draw an explicit linear fit curve to verify and draw the residuals using PlotFit elements. Here, we don't see much variation as we did with the other categorical variables either. The pattern seems to also hold for flawless category. And so, you know, it's probably safe to assume that a big portion of the variation we were seeing is being contributed by clarity. What is interesting to me is that even though clarity is a technical metric in terms of the number of inclusions and all that, it seems to also subjectively bring out the beauty in a diamond more than some of these other factors. That is an interesting insight for me from this data set. From a data analysis and modeling point of view, this is, of course, just the beginning. The main motivation for this talk is to show how the fit plots work and demonstrate the fitting options. But one can do further analysis and modeling on this data as well. And these models can be plugged into PlotFit option directly to draw the fit curves and confidence bands and residuals, all of which work as long as valid model is applied to the plotting function. Here we're doing a linear model fit on the log transformed prices and generating a fitted model. And this fitted model contains a best fit line in addition to other information. So we can plug this model into PlotFit and draw the various PlotFit elements if we wanted to. In this case, it is the same as using the PlotFit elements linear option, but one can imagine trying to construct a custom model. So here I'm constructing a model to explore the relationship of carat to price, or more precisely, to try and see if the size of the diamond matters as much as the weight. And we can plug that model in and test it to see if it works visually. And it seems to work pretty well in this case. We can also do multi-variable correlations and fits because we have a dedicated listFitPlot3D, and we also support PlotFit and PlotFitElements in a few functions like listPlot3D, listDensityPlot, and listContourPlot. I didn't use them in this talk up until this point because multi-variable correlations are not quite easy to draw inferences from. And probably more importantly, the fitting functionality in the 3D plots is going to be changing in the near future. Having said that, I will go ahead and show you what they currently look like and how they can be used. Here I'm using listFitPlot3D with the same diamonds data to plot price, table, and depth of a subset of diamonds. We're using the automatic local fit, which works in the multivariate case as well, and plots the mean surface. We're also using PlotFitElements to plot the 95% confidence envelopes, as well as the data points. I am also specifying an extra sub-element for band surfaces, which we call pillar points, and they are the grid of columns that you see between the confidence surfaces. The point of these pillars is to give the user a visual aid for depth perception. With multiple fit elements in a plot, especially in 3D, it's not always easy to place the various elements in 3D space and form an accurate visual impression. So we hope the pillar points give a sort of reference grid for you to be able to visually separate the various elements when you're working with these plots. The second plot here is plotting a subset of carat price and depth from the original data. And here is an example of generating 3D fit plot using listFitPlot3D and the corresponding PlotFit and PlotFitElements options. In this case, we are plotting depth percentage, width, and table percentage of a subset of diamonds. And we're also plotting residuals to the fit surface. Currently, we are also supporting fitting options in listContourPlot and listDensityPlot, but it's very experimental and they're going to change in short order. I've included them here for completeness. What they currently do is to visualize the fitted surface. There is also a way to make the data points visible using PlotFitElements. In the future, they may change to apply the fitting to the contours rather than the data. So these plot the same variables as the 3D plots from the previous slides. Another way to visually explore data with multiple variables is to do multi-panel plots. This is also an area of ongoing work for us, so you'll see improvements and new features in future versions. However, we did introduce a set of experimental functions in version 14 to quickly visualize multi-variable correlations. These are the pairwise plots, and they plot columns of data against each other. So for example, if we look at the diamonds data and do a pairwise list plot of all the quantitative columns, then we get a plot like this. This is probably the plot I'd have started with if this was a talk on data exploration, because this shows you at a glance how the different variables relate to each other. We can then pick out the more interesting pairs to drill in. For the purposes of this talk, the interesting thing is that the pairwise plots also support fitting options. So here is an example with the pairwise fit curves drawn. Pairwise plots provide a natural entry point for visual data exploration and are amenable to deeper analysis of the data. For example, here I'm slicing the diamonds data such that we get the counts of diamonds for each clarity grade grouped by color. So if we quickly do a bar chart of the diamonds of the highest clarity grade, by color, then we can see that we have the maximum number of flawless diamonds in the middle of the color scale. Pairwise plots are perfect to study the pairwise distributions of data and their shifts. So if we do a pairwise list plot of these data and add fit curves, then we can see that it's quite useful to compare the data against your model. In fact, it's quite similar to pairwise quantile plot with a reference line where by default we're comparing to the normal distribution. That brings me to the end of my talk, but before I finish, let me take a minute to talk about some future directions for data fitting in plots. We are planning to support fitting in more data plotting functions. One can imagine plotting data like diamonds data using other plots and charts that may yield useful insights. So here are a few examples of how I can plot some interesting aspects of the data using other plots. And some of them may benefit from having a way to draw fitting information. The other thing is, as I mentioned, some of the 3D fitting behaviors are going to change, and new plotting functions that we'll be adding in the future will also be supporting fitting features. And finally, there is ongoing work to overhaul our statistical data modeling framework, and Julia will be talking about that tomorrow. We will have a lot more models and more powerful ways to construct models, and those features will be made available from the plotting function, so you can use them directly in plots. So those are some of the things I wanted to show you today, and hope you enjoyed the talk. Have a great rest of the conference, and maybe I'll catch you at one of the visualization office hours. Thank you.